We will now look at the properties of graphs. And before we start, as a reminder, how we do mathematics. So number and copy the examples and ask your tutor or teacher if there are any steps that you do not understand. Number the questions, and unless you have the ability to get fit while watching someone else run, you must do the questions on your own before watching the answers. Mark your answers if it is incorrect. Write down the corrections and make sure you understand where you went wrong. This will enable you to do better the next time you attempt a similar sum. Now the overview of this video, the first thing we're going to look at is intercepts, stationary points, and points of inflection. And then we're going to apply the above to see where a graph is positive or negative, increasing and decreasing, or concave up or concave down. And then finally we'll look at multiple conditions. Now to start off with the properties of a graph, we are mainly going to look at cubic functions. And a cubic function has the basic form as follows, and the variables a, b, c, and d all represents numbers. And you can also see a cubic function has the highest power of 3. Now the first property that we're looking at is if the value of a is positive, then your graph ends positive. So you'll see, I like to think about it that it ends with a smiley face. That's just a interesting way, or easy way actually, to look at it or remember it. And if your a value is negative, then your graph will end with a sad face, or end by decreasing. Now if we look at the x-intercepts, the x-intercepts are basically where your graph cuts the x-axis, and that's also where your graph's y value is 0. Then, if we look at where the turning points are where your graph turns, or where it has its local maximum or minimum. And then finally, we have the point of inflection. And that's basically where the concavity changes from concavity up to concavity down, depending on what value your a is, if it's positive or negative. Now, to find the x-intercepts, what you do is you simply equal your equation of your function to 0, and then you solve for x. And same with turning point, you just take the first derivative of your function and equal it to 0, and then solve for x. And finally, the point of inflection, you take the second derivative of your function, equal it to 0, and solve for x. Now to look at how we apply the previous to an actual graph. The question says that we have to determine, for the graph of fx, determine the x-intercepts, the stationary points, and the point of inflection. So to start off with a, we know we have to find the x-intercepts, we need to say fx equals to 0. So basically I'm going to substitute in my graph there. So I've got x to the power 3 minus 11 x squared plus 23 x plus 35 equals to 0. Now this has a lot of algebra involved, because what we need to now do is we have to factorize and then solve for x. And in this case we have to factorize a cubic function. So the first thing you do when you start with factorizing a cubic function, you need to find one of the factors. And that you do with trial and error. So basically what you're going to do is you're going to type into your calculator, and I'm only going to do this once. To save time, I'm going to just give the factors in the next questions and examples. But to find the factor, you're going to start by typing in a root. So you start with, let's start by testing x equal to plus or minus 1. Then you test plus or minus 2. Then you test plus or minus 3. And then you go on as like substituting in the x values until you get until the function equals 0. Now the factor for this one is x plus 1. So that means the root is minus 1. So if I factor in, or if I substitute in minus 1, so this is to the power of 3, minus 11, then negative 1 squared plus 23 negative 1 plus 35. Right, so see, when I factored in, or when I substituted in negative 1, I got 0. So you're going to substitute in, because I knew this is minus 1. You substitute in plus and plus 1. If it's not equal to 0, you substitute in minus 1. If it's not equal to 0, you substitute in plus 2, and so on, until you get the factor. Alright, so now, if x equals to 1 is a root, that means that x plus 1 is a factor. Okay, so I think this is a tedious process, and but once you found your factor, the rest is quite simple. So if we have to now use the factorization, remember there's 3 types of factorization. We've got the pipe method, and then we have long division, and then we have the matrix method. So what I'm going to do is the matrix method, and that's just the fastest method, and in my opinion it's also the easiest method. So you draw these lines. Now what you do is you're going to draw, you're going to write the coefficients in. So we've got the coefficient of x cubed is 1, so I write it there. Coefficient of x squared is negative 11. Coefficient of x is 23, and finally the constant is 35. So you fill the coefficients in here. Then you write your not the factor, the root, you write over here as minus 1. And then you start with 0 and you have to end with 0. Now what you do now is you add down, so 1 plus 0 is 1, and then you multiply up, or to the side. So minus 1 times minus 1 is negative, minus 1 times 1 is negative 1. Then you add down again, so minus 11 minus 1 is negative 12. We multiply again with our roots. Minus 1 times negative 12 is positive 12. We add down, so this gives me 35. Multiply negative 1 with 35 gives me negative 35. And this 35 minus 35 gives me 0. So if it doesn't give me 0, then something is wrong. So it has to end with 0. Okay, so what happens now with this new numbers that we have here, this will now become your coefficients to the other factor. So in other words, if x is equal to, so this is your one factor, so that's going to be x plus 1 here. And then your second bracket, we've got x squared, so this is the coefficient of x squared, that's coefficient of x, and that's your constant. So this becomes 1x squared minus 12x, and then plus 35. Okay, now we've done that factorization, so now we're still left with this trinomial factorization over here. So I take the factors of 35 and I say, what can give me negative 12? So factors of 35 that can give me negative 12 is 5 times 7. So just copy this. Then I say x minus 5 and x minus 7. So I'm assuming that you can factorize like this at this stage. All right, so here we have this now. So if this is equal to 0, like we were solving it up here, then it means that x is equal to negative 1, or x is equal to 5, or x is equal to 7. I skipped a step there, but this means x plus 1 equals to 0, or x minus 5 equals to 0, or x minus 7 equals to 0. And then x is equal to negative 1, x equal to 5, or x is equal to 7. And this then is our x-intercepts. Okay, and then for question B. Now the stationary points, or the turning points, remember what we had to do? We had to find the first derivative and equal it to 0. So the first derivative of our function is then 3x squared So if I derive this, 3 times by 1 is 3, minus 1 is 2, then minus 22x plus 23. Okay, so now we can try and factorize this, but I know that this can't factorize, and I've also, to save time, I'm not going to look for the factors and try and factorize it. If we see that it can't factorize, you immediately go to the quadratic formula, which is x is equal to minus b plus or minus the square root of b squared minus 4ac over 2a. And then we substitute in the values of a, b, and c. Remember, this is your a, your b, and your c. So this is then equal to negative, so this is negative 22 plus or minus, so b squared again, negative 22 squared minus 4, a is 3, and c is 23, over 2, and the a value is 3. Okay, so now I'm just going to substitute this into the calculator. So this minus and minus becomes plus, so I'm just going to say 22, start with plus, my square root. Now very, very important is that you apply brackets here, minus 22 squared, because otherwise it would change the value, minus 4 times 3 times by 23. And that's all over 2 times 3, which is 6. Okay, so to 2 decimal places, we've got 6,07. And then, or for the negative parts, I'm just going to change the plus to a negative. SD. So this is 1,26. Right, so there we have the x values of our stationary points. And remember, to get the stationary points, we need to find the coordinates. And this is still only our x coordinates. So to get the y values, I substitute in my x coordinates into my original function. Okay, so I say 6,07 cubed minus 11, 6,07 squared plus 23, 6,07. Okay, so this is also quite tedious. Then we type this in. So at this point you can maybe fast forward a bit, because I'm just going to type this in quickly. So that's 6.07 cubed minus 11, 6.07 squared plus 23, 6.07, and then plus 35. Okay, so this gives me negative 7,04 if I round off to 2 decimal places. So we've got negative 7,04. And then for the other x coordinates, we substitute that one in, 1,26, and equals to, so 1,26 cubed minus 11, 1,26 squared plus 23, 1,26 plus 35. Okay, so I'm just going to replace these guys with 1.26, just to save time. 1.26 1.26. So this is 48,52. Right, so the coordinates then are, the x coordinate for that one is 6,07 and the y is negative 7,04. And then my other coordinate is 1,26 and 48,52. Right. Now finally, to get the points of inflection, we have to find the second derivative of our function. So we've got the second derivative, and we just erase the first derivative. Let's basically, because this is quite quick, let's just get the first derivative first again. So we have 3x squared minus 22x plus 23. And then to get the second derivative, it's 6x minus 22. Okay, and we want to take the second derivative and equal it to 0. That's how we get the point of inflection. So I say 6x minus 22 equals to 0 and solve for x. So then say 6x equals to 22 and x equals to 22 over 6. Then just to get the y value, we can substitute that value into the original graph. We have 22 over 6. Then we get 560 over 27. Let's just write this out. So substituting into our original graph, we'll get 22,6 over 3, or to the power 3 minus 11, then 22 over 6 squared plus 23, 22 over 6 plus 35. All right, then the answer was 560 over 27. Okay. Right, so let's see if you got this one. So question 25.1, for the graph of fx, determine the x-intercepts. So to get the x-intercepts, I'm going to take my graph and equal it to 0, and then solve for x. So I've got x cubed minus 3x squared minus 6x plus 8. Okay, so equal to 0. Now the factor, x minus 1 is a factor. And that means I draw my lines like this. It is a little unneat, but we'll still get the job done. Alright, so the coefficients of this graph here, we've got 1, then we get negative 3, then negative 6, and plus 8. I start with 0, I end with 0. 1 plus 0 is 1, 1 times 1 is 1. Minus 3 plus 1 is negative 2, minus 2 times 1 is minus 2. Negative 6 times by negative 2 is negative 8. Negative 8 times by 1 is negative 8. And I get 0. So now I'm going to say fx is equal to x minus 1. And then this is the second bracket, x squared minus 2x minus 8. And then to factorize this part, we have factors of 8 is 2 and 4, which can give me negative 2. I have to say x minus 4 and x plus 2 to get negative 2. And then if this is equal to 0, it means that x minus 1 equals to 0, or that x minus 4 equals to 0, or that x plus 2 equals to 0, which then means that x is equal to 1, or x is equal to 4, or x is equal to negative 2. Now just for one thing additionally that I didn't mention earlier is if they ask you for the x-intercepts, this is where you stop. If they ask you for the coordinates of the x-intercepts, you have to give it in the form of 1 and 0, because the coordinates of the x-intercepts are where x is 1 and y is 0. And the other coordinates would then obviously be 4 and 0 and negative 2 and 0. Okay, so then finding the stationary points, the turning points, we have to find the first derivative and equal it to 0 and then solve for x. So my first derivative is equal to 3x squared minus 6x minus 6. So then we take the first derivative and we equal it to 0. So 3x squared minus 6x minus 6 equals to 0. And we solve for x. So let's simplify this by dividing every term with 3. So we've got x squared minus 2x minus 2 equals to 0. Now this can't factorize, so I'm going to substitute it into the quadratic formula. So x is equal to minus b plus or minus b squared minus 4ac over 2a. Right, so we substitute in our a, b, and c values. X is equal to negative, so this b value is negative 2 plus or minus square root of negative 2 squared minus 4, so the a value is 1 and the c value is negative 2 over 2a, so 2 times 1. Right, so what I'm going to do before I type this into the calculator, I'm just going to simplify it first. So we've got minus minus is 2, plus minus square root of negative 2 is 4, plus 4 times 2 is 8. Now, I just prefer to simplify it a bit more because typing it in with all those brackets takes quite a lot of time. All right, so we've got 2. Let's start with 2 plus, and then the square root of 12 over 2. So this then is 2,73. So x is equal to 2,73, or x is equal to, then if I change the plus to a negative, I get negative 0,73. Right, now to find the y coordinates, we substitute it into our original graph. So f, I'm just going to start here for space. So f of 2,73 is equal to, now that is going to be 2,73 cubed. Now, as I mentioned before, here you can actually fast forward until I've done all these calculations. So this is squared minus 6, 2,73 plus 8. All right, and then this gives us, right, so I'm just going to type this in, 2,73 to the power of 3 minus 3 times by 2.73 squared minus 6 times 2.73 plus 8. So this is negative 10,39. Right, and then for the other coordinates, if I substitute in negative 0,73, so we say negative 0,73 cubed minus 3, negative 0,73 squared minus 6, negative 0,73 plus 8. Okay, so just to replace these values, $10,39. Okay, so that means then my two coordinates are going to be 2,73 and negative 10,39, and then the other coordinate will be I'm just out of space here. The other coordinates will be negative 0,73 and 10,39. Okay, so now for the point of inflection. The point of inflection, we need the second derivative. Okay, so let's just quickly find the first derivative again. We've got 3x squared minus 6x minus 6, and then the second derivative is equal to 6x minus 6. Alright, and then if I solve for x there, if I equal this to 0, and then solve for x, so 6x is equal to positive 6, divide both sides by 6, x is equal to 1. And then to find the coordinate there, we substitute in 1 into our original graph, so that's f1 equals to, so 1 power 3 minus 3 times by 1 squared minus 6 times by 1 plus 8. Okay, so this is just 1 minus 3 minus 6 plus 8, so this is minus 9 plus 9, so this is equal to 0. So my coordinate of my point of inflection will therefore be 1 and 0. Okay, now for question 25.2, we have the same question again, just another practice question. So to find the x-intercepts, remember we say we take our graph and we equal it to 0. Therefore, we have 2x to the power 3 minus 7x squared minus 5x plus 4 equals to 0. So at this stage, you type in plus and minus 1, plus and minus 2 until you get the factor or whatever equals to 0. And the factor is x plus 1 is a factor. So if you typed in minus 1, then this expression over here would be equal to 0 if you typed in minus 1 for x. So x plus 1 is therefore a factor. Okay, so now I draw these lines again. Okay, so I put my minus 1 here. My coefficients goes 2, minus 7, minus 5, and 4. And then I start with 0 and I end with 0. Right, so I add down, so that's 2, multiply across, minus 1 times 2 is negative 2, this is minus 9, this is plus 9, and then this is 4, and then minus 1 times 4 is negative 4, so we get 0. So that means my function in its factored form will be x plus 1, and then 2x squared minus 9x plus 4. Alright, so now I need to factorize this. Let's just draw our factors over here somewhere. So I have 1 times 2, and on this side we have 1 times 4 and 2 times 2. And then we can swap around this side, so 2 and 1, because we need to get minus 9. Now to get negative 9, if I say 2 times 1, I get 2, and 1 times 4 is 4. So 2 and 4 can give me 9. Next, I can say 2 times 4, which is 8. And 1 times 1 is 1. To get negative 9, I must say minus 8 minus 1. So this negative goes over here. This negative goes over here. So you have 2x minus 1. Okay, so you just write the x plus 1 down. So you have 2x minus 1, and for this factor we have x minus 4. Right, so if that is equal to 0, it means that x plus 1 equals to 0, or 2x minus 1 equals to 0, or x minus 4 equals to 0. So x is equal to negative 1, or 2x, or x is equal to a half, or x is equal to 4. And that is then my x-intercepts. Okay, so let's do B. And B says stationary points. So for stationary points, we need to find the first derivative of our graph and equal it to 0. So my first derivative then is equal to 6x squared minus 14x minus 5. Okay, and this one can't actually factorize, so therefore I'm going to use the quadratic formula. So x is equal to negative b plus or minus b squared minus 4ac, square root of that, over 2a. Okay, substitute in. So here we have negative 14 minus negative 14 goes in, plus and minus square root of negative 14 squared minus 4. A is 6 and c is negative 5 over 2 times by a, which is 6. Right, and then let's type that in. So minus minus is plus, so I'm just going to say 14 plus square root of, now brackets is important, minus 14 squared minus 4 times by 6 times by negative 5. Over 12. And that gives me 2,65 if I round it off to 2 decimal places. Or x is equal to, so replace that with a minus, then we get negative 0,31. Okay, so now we want the coordinates. So to get the y values, we substitute into our original graph, 2,65, and that is then 2 times 2,65 cubed minus 7, 2,65 squared minus 5 times 2,65 plus 4. Okay, so we have 2 times by 2.65 cubed minus 7 times by 2.65 squared minus 5, 2.65 plus 4. And that's equal to negative 21,19. Right. For the other coordinates, we have negative 0,31, and I substitute that in. 0,31 cubed plus, not plus, minus 7, negative 0,31 squared minus 5 times by negative 0,31 plus 4. Okay, so this time I just have to replace it and have to type everything over. Minus 0.31 okay, and that's equal to 4,82. Right, and then the coordinates obviously is just our x coordinate was 2,65 and negative 21,19, or the other coordinate negative 0,31 and 4,82. Okay, now finally for the point of inflection. So C, we need the second derivative. So the first derivative was equal to 6x squared minus 14x minus 5. And then the second derivative would be equal to 12x minus 14. So if I equal that to 0 and solve for x, then x should be equal to 14 over 12. And just to simplify that, x is then equal to 7 over 6. And then to get the coordinate, we substitute in our value for x into the original graph, and that will then be 7 over 6 cubed minus 7 times 7 over 6 squared minus 5 times 7 over 6 plus 4. And let's type that in. We already have our graph here. Okay, and that's negative 221 over 27. Okay, so those were intercepts, stationary points, and point of inflection. Let's look at applying these to our graphs. Now, where do we use intercepts? We know now how to find intercepts. Where would we want to use it? So intercepts is where the graph, or where we're going to use it is to see where is the graph positive or negative. Because if I find my x-intercepts, the graph will become positive or negative when it crosses one of my intercepts. So if you look at this graph, for example, the red area is where the graph is positive, meaning where does the graph lie above the x-axis. Then your y values or your fx values will be positive. And then similarly, where is the graph negative? The graph is negative when the graph lies below the x-axis, because that means your y values will be negative or your fx values will be negative. Okay, so now if we have certain values like a, b, and c is just variables that represent numbers, if we know these values, and we've actually now just seen how to calculate these values by solving the for the x-intercepts by just equating your normal function to 0 and solving for x. The question will say where is the graph, or they can actually put this into the question, where is fx greater than 0, just meaning where is your graph positive. And you're gonna have to give your answer in terms of x. Okay, so we can see that from A to B we have a positive graph, and then also here it becomes negative, and then from C onwards it's also positive. So if I need to say this in mathematical terms, and in terms of x, everywhere where x is between A and B, so being less than, if I just write that down, these points here, it would be where A is less than x and x is less than b, between A and B, or where x is greater than c, meaning from c onwards up until infinity. Okay, so now let's look at the negative parts. The negative parts is the blue part, so our x values will be here where wherever x is less than a, or whenever x lies between b and c, the graph will be a negative value. So if we look at how that is represented in terms of x with the notation, it says that x is less than a, or where b is less than x and x is less than c, meaning x lies between these two values. Okay, now where do we use our stationary points, or for what? And then we can use our stationary points to show us where the graph is increasing or decreasing. And remember, how to check if a graph is increasing or decreasing is quite simple. If you move your pencil from left to right over the graph and you're going up, that means you're increasing. The moment you're going down, you're decreasing, and the moment you're going up again, you're increasing. Now, what's special about the stationary points is the graph is neither increasing or decreasing at the stationary points. They are stationary. That's why they are actually called stationary points. And if we look at where's the graph increasing, the red parts, we can clearly see that we're going up here and up here from negative infinity to the stationary point, and then again from the second stationary point up to infinity. Okay, and then where's the graph decreasing? It's from this stationary point going down till this stationary point. Okay, so if we have to represent that or write it algebraically, and our station points, we just saw also how to find our station points. We'd get the first derivative, equal it to 0, and solve for x, and then these are the two x values that you find. This is what you actually find when you find those two x values. And remember, a and b just represents a number. Okay, so if we are asked, you can either be asked where is your graph increasing, okay, and then you obviously know, if you're asked where is your graph increasing, then you need to find the first derivative and solve for if the first derivative of x greater than 0, or they can actually just give you this notation and say determine the x values for which this f1x is greater than 0. So what you're going to do then is to do a rough sketch of the graph, but we'll actually look at some examples. But to represent this, then if you found your values, is then to look at the graph and see, okay, after I found my values, I can see also graphically where is it increasing. Then when it's increasing, when it's these values here, we'll say that it's where x is less than a. And on here, we can see that the graph is increasing here, so it's obviously where x is greater than b. So the hard work is actually the previous section that we did to find these a and b values, but that's just simply by finding the first derivative and equaling it to 0. And then you just plot them on your graph and look at where are we increasing and where are we decreasing. So similarly for the decreasing part, we can see that from this turning point up to this turning point, the x values that lie between a and b is where the graph is actually busy going down or decreasing. So we'll write that as a is less than x and x is less than b, once again just saying that x lies between a and b. Now for the point of inflection. The point of inflection is the point where the graph changes concavity. So that with that we can answer the question that says, where's the graph concave up or concave down? And once again, we saw how to find this point of concavity by taking the second derivative of our graph, equaling it to 0 and solving for x. Now, when a graph is concave up, or when the second derivative is greater than 0, meaning positive or concave up, the graph is, and once again, a very simple analogy, the graph is smiling. Okay, and then when is the graph concave down? From the point of inflection, it's where your graph is crying or has a sad face. Okay, so now if you found the point of inflection, so you notice that we only got, whenever we solved for the second derivative, we always only got one answer, and that's because there's only one point of inflection on your graph. So once you have the c value, if they ask you where's the graph concave up, then obviously you know you have to relate concavity and point of inflection with each other. You basically find the point of inflection like we did in the previous section, and then you'll from your graph that you draw, and remember, you draw your graph by using the a value. If the a value, just a reminder from the very first thing we did in this video, if the a value is positive, then, so if a value is positive, then your graph looks like this, and if your a value is negative, then your graph looks like this. So if you have your point of inflection like here and here, then this part will be concave down, whereas if your a value is negative, this part will be concave down. So that's just a small thing to look at, very important, but quite simple. Okay, so let's start with this guy. If they say, where is the second derivative greater than 0, it's the same as asking where is it concave up, and they can ask it either way. So then we can see the x values that applies to the graph being concave up is here, everything that's greater than c. So x is greater than c, so whatever you found for your value, like if you find 2 or 3, then you just say x is greater than 2 to be concave up. And then for the concavity to be negative is everything that's less than c. It's where x is less than c, that's where your graph is concave down. So notice it's not always that if the first derivative is greater than 0, that x is going to be greater than c. That you determine by looking at this. Okay, so if your a value of your original graph is positive, you know you're concave down on this side, and if it's negative, you're concave down on that side. Just remember that. So for example 26, we're given this graph of fx for which values of x is the graph positive, or they can ask where is fx greater than 0. So basically, first thing I'm going to do, now we're going to have to go through all the steps that we used to do with the previous section. So before I can, to find where my graph is positive, now also let's notice that this graph has a positive a value. So it's good to start off by just drawing a rough sketch of our graph. So if it has a positive a value, we know that it ends positive. So it's going to look like this, all right? And we need to find the intercepts to be able to find where is my first, where is my graph positive. Remember, we need to find the intercepts, because the intercepts tells us where it changes from negative to positive, from positive to negative, and so on. So that means I need to say if x equals to 0 and solve for that. So I'm going to say x to the power 3 plus x squared minus 16x plus 20 equals to 0. Okay, so here we have to do all those calculations again, where we're going to factorize. And the factor here is x minus 2 is a factor over here. All right, and then, so this is just a, let's just do that. So to factorize, I'm using the matrix method. So the 2 goes there, and our coefficients is 1, 1, negative 16, and 20. We start with 0 and we end with 0. We add down, so it's 2 times 1 is 2, then we have 3, then we have 6, then we have negative 10. That times by 2 is negative 20, so we get a 0. All right, now the factors will be x minus 2, and the other factor will be x squared plus 3x minus 10 equal to 0. So x minus 2, and then x. So factors of 10, that can give me 3. This can actually factorize. So that's a bit easier, and a big relief that we don't have to actually use the quadratic formula again. So we have 2 times 5. So this is plus 5, and x minus 2 equal to 0. Right, so that means that x is equal to 2, or x is equal to minus 5, or x is equal to 2. Okay, this is quite a special case, because what happens here, I have to actually redraw it, because both of these, can you see there's a 2 there and a 2 there? So that means this intercept here is at negative 5, but both of these intercepts are at 2, meaning it looks something like this, where we have our graph, but then it goes, the one coordinate, the one turning point falls on the x-axis, because both the intercepts fall on one point. So this is what it looks like. So if we have, this is then our 2, and this is then we're minus 5 lies. Okay, and now if we actually have to see where is fx greater than 0, can you see that this whole graph is actually from -5, the whole graph is actually lying on top of the x-axis. So all of this values here is positive. But just be careful, because this says greater than 0. At this point here, it's actually equal to 0. Okay, so this is where because this is your y-axis. So this, everything on the y is 0 over here on the x-axis. So everything is positive except at x equals 2. So therefore, we can either write it, we can write it in two ways. I'm going to write it in both ways. So we can say that we're between -5 and 2. So -5 is less than x, and x is less than 2. And where x is greater than 2, so all of this is this part, and then greater than 2 is here. Or I could have written it as simply saying that x is greater than -5. Okay, so for all the x values from here, not including x, it's positive. See, graph is above for all those values. But x does not equal to 2. Okay, because at 2, at that point, it's actually equal to 0. If the question said where's fx greater than and equal, like if it looked like this, fx is greater than and 0 and equal to 0, like this, then we wouldn't have had to put this in place, because then it would also include this 2, which is equal to 0, where the y value is equal to 0. All right, but now we are focused on that guy, and I would I think this is the best way to write it, just my personal opinion, but both of these are correct. Okay, so now for B, for which values of x is the graph decreasing? Okay, so we know now what the graph looks like. So it's something like this, where we have the graph going through here. Okay, and we need to now find, because we found our intercepts, we need to find this point and this point. Now actually we already have the one turning point, because this was 2. The turning point was the x-intercepts. So, but to follow the normal procedures, increasing and decreasing has to do with the first derivative. So to find the first derivative and equal it to 0, the first derivative of our graph is 3x squared plus 2x minus 16 equal to 0. Right, so to factorize this guy, this looks like a lot of factorization. So I have 1 times 3 and 1 times 16, 2 times 8 and 4 times 4, because we need to get plus 2. Okay, so we can swap these guys around. So I'm going to say 1 times 16, and that's not going to give me 2, that's a bit big. Then I've got 1 times 8 and 3 times 2. So 3 times 2 is 6. 1 times 8 is 8. To get plus 2, I'm going to say plus 8 minus 6. So this negative goes over here. This plus goes over here. My factors then is x minus 2 and 3x plus 8 equal to 0. So this means that x is equal to 2, or x is equal to negative 8 over 3. Okay, so this makes very much sense, because we already know that one of our turning points is at x equals to 2. So that means this other turning point will be at negative 8 over 3. All right, so the graph says the question says where's the graph decreasing. So we see that it's increasing here, but it's decreasing here. So it means it's and remember, it's neither increasing or decreasing on our stationary point. So it is where minus 8 over 3 is less than x is less than 2. Now this is the easy way. If you if you get confused with saying less than or greater than, just remember if a value lies between 2 points, any 2 points on the x, so if we have like A and B and you need to describe a value or this region over here, just always say A less than x less than B. So that you always use the less than sign. That just represents a value between these 2 points, because this is something I've seen a lot also, and that's just that's wrong. Okay, don't do that. This is to describe x between 2 points. Okay, so that is actually now our final answer. Okay, so let's move on to C. So C, for which values of x is the graph concave up? Okay, so once again, just rewrite this, redraw this. So this was like this. So concavity, point of concavity lies somewhere there. And so first, remember we need to find the second derivative for concavity now. First derivative was 3x squared plus 2x minus 16. Then the second derivative is equal to 6x plus 2. And we solve for the second derivative, putting that equal to 0. So 6x plus 2 equals to 0. If I solve for that, x is equal to negative 2 over 6, which simplifies to negative 1 over 3. All right. So that means this point of concavity is negative 1 over 3. Okay, so that actually lies on this side. But you get the idea, I hope. So where is it concave up? Now remember, concave up means positive, means smiling. So this part over here is where it's concave up, and it's for all the x values that's greater than negative 1 over 3. So I'm simply going to say where x is greater than negative 1 over 3. Question 26.1. Given the graph of fx for A, for which values of x is the graph negative? Or in other words, where is fx less than 0? Right, so what we need to do is find the x-intercepts. Okay, so in this case, because if I find my graph, let's just do a, because this A value is positive, my graph will end positive. And we need to find the intercept. So wherever the intercepts would lie on this graph, that could tell you from where to where is it positive or from where to where is it negative. So first thing we're going to do is we're going to take our normal graph and equal it to 0 and solve for x. So I've got x cubed plus 4x squared minus 3x minus 18. All right, equal to 0. So now we have to factorize, and we start by finding the first factor. We do that by substituting in plus or minus 1, plus or minus 2, plus or minus 3. Just to save time, I'm going to immediately say that the factor is x minus 2. So that is the factor, is a factor. There's actually 3. All right, and then to use the matrix method to find the, or to factorize it further. And we have our coefficients as 1, 4, minus 3, and negative 18. And then our factors root goes over here. So we start with 0 and we end with 0. 1 plus 0 is 1. 2 times by 1 is 2. If I add down, I get 6. Times by 2 is 12. Add 12 to negative 3. We get 9. Times by 2 is 18. So here we have negative 18 plus 18, and that does give us 0. All right, so my factors then, the first one was x minus 2. And then this is my new factors for my quadratic factor. So that's going to be x squared plus 6x plus 9 equal to 0. All right, so to factorize this further, quadratic or trinomial factorization, we can just apply that there. So then we get x plus 3 and x plus 3, because the factors of 9 is 3 and 3, and to get plus 6 I must add them. All right, so that's 0. So therefore we have that x is equal to 2, or x is equal to -3 or x is equal to -3. And this is one of those special cases again where we have actually two intercepts at the same point. And what does that mean? That means that that we are going to have a turning point on the intercept. So now we have to also look at where does this turning point lie, because now we know our normal graph. If I just draw it slightly bigger over here, remember this graph, I'm going to shift it up and down just to get the basic form of it, now knowing that it has a turning point on the graph or on the x-axis and that it has another intercept at 2. So we know that -3 is less than 2. So the meaning, if I have to choose between which one is going to lie on the x-axis, so I can move it up and put this turning point over there, or I can move it down and put this turning point over there. And remember, there is a correct one and a wrong one. And if I move it up, right, and I put my turning point here, then my other intercept will be here. And that is actually wrong because 2 is actually bigger than 3. So I need to move it down, meaning it needs to now lie like this, so that here we've got -3 where both of the intercepts happen, and here we've got 2 where the other intercept is. So now I can look at my graph, and if the question says where is fx less than 0 or where is it negative, where does my graph lie beneath the x-axis? So remember, this is my x-axis. Where is my graph beneath this x-axis? And if I look at this, it goes on forever. This is just going negative and negative more and more. So meaning only here does it actually become positive. So this is positive values. All of this is negative values, except for this point here. This point is actually equal to 0. And it doesn't say less than or equal to 0. It only says less than 0, meaning from -2, all the x values less than -2 is actually below, except for that one. So if I write that, I'm just going to say that where x is less than 0, so that just means all of this, guys, all of this, and then but I have to include that x is not equal to -3, because at -3 it's actually equal to 0. Right, so let's look at B. Now for B, says for which values of x is the graph increasing? Okay, and remember when we had our graph increasing, we do that by finding the turning points. And we find the turning points by finding the first derivative and equaling it to 0. Okay, so the first derivative of our function is equal to 3x squared plus 4x minus 3. Okay, so if I equal that to 0 and solve for x, I have 3x squared plus 4x minus 3 equals to 0. To solve for this, I need to factorize it. So factorizing, we can use this method. Factors of 3 is 1 and 3. And on this side, 1 and 3. And I'm just going to swap this side around, 3 and 1. I need to get 4 plus 4. So this one's going to work. If I say, oh wait, this is then going to be 3 times 3 is 9, so that's not going to work. Alright, so it seems like it can't factorize. So in that case, I actually did an error here. I made an error here. This is 2 times 4, which is 8. Okay, so we actually need to get plus 8. Okay, so if I say 3 times 3, it's 9, and 1 times 3, 1 times 1 is 1, 8. To get plus 8, I need to say plus 9 minus 1. So this negative goes over here, and this plus goes over here. So I've got 3x minus 1, and I've got x plus 3 equal to 0. So x is equal to 1 over 3 or x is equal to -3. Alright, so we look at our graph here, and this -3 we already knew was a turning point, and then this 1/3 here is the other turning point. 1/3. Okay, so now from the turning points we can distinguish this is going up, this is increasing, then decreasing, then increasing, and we are interested in where is it increasing. So all the x values that are less than -3 are actually from left to right increasing. Then again we're going down, and then here increasing. So all the x values that are greater than 1/3 is increasing. So my answer then is going to be where x is less than -3 and where x is greater than 1/3. And that's the answer for B. Okay, so next one we've got C. And it says, for which values of x is the graph concave down? And remember, concavity has to do with the second derivative. And our graph's form was like this. So to find the first derivative was equal to 3x squared plus 8x minus 3. Okay, and therefore the second derivative will be equal to 6x plus 8. And then if I equal that to 0 and solve for it, I've got 6x plus 8 equals to 0. So take the 8 over, 6x is equal to -8. So x is equal to -8 over 6. If I simplify it, I get -4/3. Right, so this point here, the point of concavity here, lies at -4/3. So we are interested in concave down, meaning the one that frowns. So this side. So everything where all the x values that is less than, so all the x values that lie here, everything that's less than -4/3, that's where our graph is concave down. So for x being less than -4/3. Alright, and that's basically the answer there. Right, so for question 26.2, given this graph, for which values of x is the graph positive? Now, let's first establish that our graph, this A is positive, meaning our graph lies like this, ending positive. And we need to first of all find the intercepts to show us where it is going above the x-axis and where is it going below the x-axis. So that means we need to find fx equal to 0, solve for fx equals to 0. So x to the power of 3 minus 12x plus 16 equals to 0. And to find the first factor, we substitute in different values for x, and the factor, x minus 2, once again, is a factor. So now I've got this going on again, my matrix method, and this is a special graph. This one is a good example because you can see we've got x to the power of 3, but then the second term, which is normally x to the power of 2, is not there. Okay, so don't make the mistake of putting in your factors here as 1 minus 12, 16. You still have to put the coefficient in for x squared. X squared isn't there, so its coefficient is simply going to be 0. This one is 1, then 0, then -12, then 16. Okay, so this one belonged to x squared, which is not there. And then we start with 0, we end with 0, and my factors, my root is going to be 2. So add down is 1, times up is 2. Add down is 2, times up is 4. Add down is -8, times 2 is -16. And then my factors, or my new factors, is x minus 2 and x squared plus 2x minus 8 equal to 0. So now I have to factorize this guy, x minus 2. So we have So if I factorize the factors of 8, which give me 2, is 2 times 4. So I'm going to say plus 4 and x minus 2 equal to 0. And once again, we actually have two factors that's the same. So once again, we're going to have a turning point on the x-axis, or x is equal to minus 4, or x is equal to 2. Okay. And once again, now we have to just decide, is it going to be this one or is it going to be this one? If my graph lies here where the x-axis is here, it means that, see, this one is the one that's the turning point, because that has two intercepts at the same point. Now, if that is 2, it doesn't make sense that negative 4 lies here. So our x-axis actually goes here, through here, where this intercept is at 2 and this intercept here is at negative 4. Okay, and we are looking for the values where the graph is positive. So it means where is the graph above the x-axis? It's all the values that are greater than negative 4. So x is greater than negative 4, but it does not include the 2. So x does not equal to 2 because our graph is actually 0 on the x-axis. Right, now we go on to B, and it says for which values of x is the graph increasing. And when we work with increasing and decreasing, we look at our turning points. So the turning points distinguish the increasing or change the increasing to decreasing and vice versa. And to find the turning points, we have to solve for the first derivative equal to 0. So first derivative of our graph is 3x squared minus 12 equal to 0. And factorizing this, we just take out 3 first. We get x squared. We can actually divide by 3. That would actually be simpler. X squared minus 4 equals to 0. Just took out a common factor. This is difference of squares, so we can factorize that as x plus 2 and x minus 2 equal to 0. So x is equal to negative 2 or x is equal to 2. Okay, so that is our two turning points here at negative 2 and we saw that it looks like this. So this is at negative 2 and this is at 2, and we knew this was at 2. And where is it increasing? So increasing meaning you're going up, then we're going down, then we're going up. So for all the values that are less than minus 2, this side, all the x values that are less than minus 2, we're increasing. So x is less than minus 2. Or for all the values that are greater than 2, we're also increasing. So where x is greater than 2. And there we have it. That's our answer. Okay, and then we move on to C. So for which values of x is a graph concave up, and the graph looked like that. So we see it is these values, so we have to find the point of inflection because that's where it starts or changes concavity. Now, first derivative of our graph, so basically we need to solve for the second derivative and equal to 0. Need to solve for that. So our first derivative was equal to 3x squared minus 12, and then our second derivative is equal to 6x, just 6x. Okay, so if I solve for 6x equal to 0, then x is simply equal to 0. So for concave up, where this is 0, for concave up, it starts going up like everything that is bigger than 0. So where x is greater than 0, that is where my graph is concave up. Okay, so we are done with that section. Now let's look at a few examples on multiple conditions. Now for example 27, we're given the graph of gx with the roots equal to 3, -4, and 5. And the question says, for which values of x will gx times the second derivative of x be greater than 0? So this is the type of questions that a lot of people actually just leave open. And once you have the sketch, it's actually not that bad. So if I start by drawing, and here we've also been given the roots, so that also makes our job a lot easier. We don't have to actually factorize and solve for x, we already have that. So if I'm just going to make a rough sketch of this, we see that the roots go through, to just draw this here, the roots go through -4, so let's say it goes here, and then at 3 and at 5. Just to roughly see what's going on there. And it also goes through this is the y-intercept at 60, so it's here at the top. And then it would look something like this, where we have our graph, because it ends positive. We see that the a value is positive, so it ends positive. It goes through 60, and it takes a turn like that, something like that. It's not very neat, but we get the idea. All right, now the question says that we have to get the values where gx, now we know where's gx positive and negative. Gx is the actual y values, so the graph is positive above the x-axis and negative below the x-axis. And then the second derivative, we remember the second derivative is the concavity of the graph, so it's negative for the first half until the point of inflection, and then it is positive for the second half after the point of inflection. Okay, so this is then -4, just to put in the values here, and 5. We still need to find this x value also for the point of inflection, since we're working with a second derivative. So to do that, we're just quickly going to find the first and the second derivative of our graph and then solve for x. But that's actually quite easy to do. So first derivative is 3x squared minus 8x minus 17, and then my second derivative is 6x minus 8. Okay, so if I solve for that, putting that equal to 0, I'll get that x is equal to 8 over 6, or simplified 4 over 3. Okay, so this value here, 4 over 3, lies somewhere there. Okay, now let's write down what we need. We need to say gx times by the second derivative being greater than 0. Okay, now these represent values, and for greater than 0, it needs greater than 0 means positive. So that means to get a positive value, if I multiply two values, for it to be positive, I can either multiply a positive with a positive, or I can even multiply a negative times a negative, also gives me a positive. So what I need to do is I need to see from my graph where is both positive and also where is both negative. So let's start with the first condition, and here we're going to use different colors. Always use different colors because this is going to get a bit messy. So we've got a plus. Where is my graph positive? My graph is positive above the x-axis, so that's here and here. All right, and just notice that it says greater than 0, so it does not include these values, which is our roots. If it said equal to as well here, you would have included the roots as well. Okay, and then just to go on to another color, where is the first derivative, the second derivative, or my concavity positive? So it's positive from here. This is where the graph is concave up. Okay, now where is both true? All right, so let's use a highlighter for that. Where is both my graph positive and my concavity positive? I can see from this part here we have both of them being positive, and then also over here both of them are positive. So if we should write that down, let's just go to the pen again. if we should write this part down, we see that it's, let me just go back there, this, here, from here to here, that's my x values. From 4/3 to 3 is where both are positive, and then from 5 onwards, also both positive. So let's put that down. It's where we have from 4/3 being less than x and x less than 3. That's my one condition. And where x is greater than 5. We also have both of these conditions positive. Right, next up we need to check where is both negative. So let's start and highlight the parts. Let's do it in red. Where is my graph negative? My graph is negative over here, and my graph is negative over here. Where is my graph concave down? So let's do it purple. Concave down from this point over here, from my point of inflection, less than my point of inflection, all the x values less than my point of inflection, that's where my graph is concave down. Okay, so where is both true? Both is true here. Here my graph is both concave down and negative. So for all the x values that are less than -4, that is where my graph is both concave down and negative. Right, so if I put that down, then I'm just going to say and where x is less than -4. These are then my conditions. This is then the answer. Where the x g of x times by the second derivative times should be greater than 0. It's all of these values then. Okay, question 27. Given the graph of fx with these roots, for which values of x will x times by fx be less than 0? Okay, so for the first one, we have our x values and our fx values. But before we start, let's just start by first plotting our values to see where the roots lie and where it is positive and negative. So first of all, I'm going to draw my graph. So here we go, and then this is at -0.5, -2 and 4, and it goes through -8. So this is going to look something like this. If I have -0.5 here, then my 2 will lie somewhere here, and my 4 would lie further on. Let's say maybe here. Okay, so this is at, and then the graph is positive, so it ends positive. So that means it's going to look something like it's going through here. Okay, so it looks like this somewhat. If I should just do the rough sketch of it. Okay, so this is at -8. Okay, and then here we have -2, here we have -0.5, and here we have 4. Okay, right, so now we also need our point of inflection over here, but let's just focus on question A for now. We want to know where is x times by fx going to be less than or equal to 0. So that means if it's less than or equal to 0, it means you either need to have a plus times a minus or a minus times a plus, because that would give you a negative. So either x must be negative while fx is positive, or x must be positive while fx is negative. Alright, so let's look at where is x negative. So once again, we're going to use different colors. So x being negative, wherever x, remember this is your x-axis, so x is positive on this side, x is negative on this side. Y is positive on the top, y is negative at the bottom. So from here, going on down like that, that's where x is negative. And then where is my graph positive? So let's just get another color again. So where is graph positive? So graph is like your y value. So my y values are positive over there and also over here. All right. Now where are both true? Highlighter. So from this point here and here, that's where both my x values are negative and my fx values or my y values are positive. So it's from this point, -2, up until -1/2, where both of these conditions are true. So if I put that in algebra, write that down, we have from -2, and notice that this says less than or equal to, so it's going to include these two values. So it will be where -2 is less than or equal to x, x is less than or equal to -1/2. All right, now the second condition, where's my x value is positive but my graph negative? So we have x values positive from there until positive infinity, going on there. And then where is my graph negative? Is this part over here, and also from here all the way there. Okay, so that's where my y values are negative. Now let's see where both of these conditions are satisfied. So we have where the graph is, where the x values are positive and where the graph is negative. So x values are positive and the graph is negative, all of these values. So it's from 0 up until this 4. Okay, so to write that down, so it's from 0 less than or equal to x, and x was less than or equal to 4. So this is then the answers, those two. Okay, so let's look at the next question, question B. Now for B, for which values of x will fx times the first derivative of x be greater than 0? So in this case, we are now interested in the first derivative. So let's first just see, and remember the first derivative is turning point. So that means what we need to find now is where are these x values over here. So first derivative is then going to be 6x squared minus 6x minus 18. And solving for that, 6x squared minus 6x minus 18 equal to 0. We can just divide everything with 6 to simplify that. That's minus 3 equals to 0. Now factors of 3 to get me -1. So this one can't factorize. That means I need to use the quadratic formula. So we have x equals to minus b plus and minus b squared minus 4ac over 2a. Let's substitute that in, so we get -1 plus and minus, so b squared is then minus 1 squared minus 4, a is 1 and c is -3 over 2 times by 1. Okay, so we'll have 1, because the minus and minus is just a plus, then plus the square root of -1 squared is just 1, and then that becomes plus 12 over 2. Okay, so this gives us 2,3, so x equals to 2,3, or x is equal to, if I just replace that plus with a negative, then -1,3. Okay, so here we have -1,3, and over here we have 2,3. And what we want to do now is use that value. So let me just make some space here. So this was negative 1,3 and this was 2,3. Right? So basically we want to find out fx times by the first derivative of x being greater than 0. So being greater than 0 means either both is a positive or both needs to be negative. Alright, so let's start with the positive values. Now for the function to be positive is over here and over here. That's where my graph is above the y-axis or the x-axis. And then where is the first derivative positive? That means where's the slope going up? So that's from here up until this point over here. And then from this point upwards that way. So where is both applicable? If we just look at where we see both the graph being positive and the slope being positive is this part over here, and then also this part over here. So that lies between a -2 and negative 1,3 and greater than 4. So let's put that down. We get -2 less than x less than negative 1,3, or at x being greater than 4. Okay, now turning to the negatives. First of all, we have the function being negative is here and here. And then where's my slope? Negative is going down from this turning point to this turning point. And where do both of these apply? It's from this turning point over here going down to that turning point. So basically what we have there is then going to look like this, where we have from negative 1,3, or actually the graph needs to be positive, so actually it's just this part over here, because the graph needs to be negative, and the turning point, the graph needs to be negative, and the first derivative, the slope, needs to be negative. So that's actually from here to here, from negative a half less than x less than 2/3. It says for which values of x will fx times the second derivative of fx be greater than or equal to 0. So once again, we saw that we now need our, our point of inflection. That's going to play a role now for the second derivative. So once again, let's just find the first derivative we saw was equal to 6x squared minus 6x minus 18. And then the second derivative is equal to 12x minus 6. If I solve then for that, putting it equal to 0, we get x is equal to a half. So that actually looks like our point of inflection is also here on oh no, wait, it's actually on positive a half. So this is actually going to be here. This is where our point of inflection lies. Okay, so this is where positive a half happens. Now, let's see. We've got fx times by the second derivative of x being greater than or equal to 0. So greater than or equal to 0 means positive, meaning plus times plus or minus times minus. And let's mark these. Where is my graph positive? My graph is positive here and here. Where is my second derivative positive, or in other words, where's my graph concave up from the point of inflection where it smiles, basically. Okay, so the only condition where both of these apply is actually here. So where we have x being greater than 4, so where x, but remember this is greater than or equal to 0, so it means it includes this root here, so it's where x is greater than or equal to 4. Now for the next set, if I say where is my graph negative, it's negative over here, and it's negative for all these values. Remember, just your negative y values. And then where is the graph sloping down? So let's use that color. Where's my graph sloping down? It's first half of the graph up until my point of inflection. And then to highlight which values apply to both, we've got here we have our graph being negative and my graph concave is concave down here. And between these two values also, from here to here, the graph is both negative and it's concave down. Alright, and then if I put that down, to write that down, we have where x is less than or equal to negative 2, and where negative a half is less than or equal to x is less than or equal to a half. Alright, and that's it. That is then our answers. Okay, and that was multiple conditions, and that means we are done.